analytic limit situation. Limit. Here's a typo for somebody. This is the incorrect title. They should say analytic limits. And the objective should change also. So those are two separate typos. So you submit those, you get a bonus point, be happy camper. All right. So limits where x approaches infinity, limits where x approaches a constant. All right, two possible scenarios. So in the case where we're looking at a limit where x approaches infinity, the first thing that you're going to do is find the end behavior model. All right, you're going to find the end behavior model. All right. Now, that's yet another topic that may or may not have happened like it should have in a pre-calc class. So I'll take you through how to do it now. It's not terrible. All right. So end behavior model, also known as EBM. It's not too difficult. All right. So to find the EBM, divide the term with the highest power in the numerator by the term with the highest power in the denominator. All right. This really only works for rational functions and polynomial functions. There is a way of determining end behavior for other types of functions. But bottom line is, if there's no numerator and denominator, then you wouldn't use this technique. It would be pretty obvious. All right. So find the limit of the EBM, the end behavior model, by substituting the limiting value C for X. All right. So whatever the limiting value is, so the limit as X approaches, what is that value? That C value. That value will get plugged in for X. All right. Now, I'll give you the technique for X approaching a constant too. Right. It's a little easier in some cases, but it can be trickier in other cases. It's kind of like the easiest X approaches a constant problem will be easier than the easiest X approaches infinity problem. Right. So if that means anything. So the technique is going to be to plug or substitute the limiting constant into f of x for x. So basically find f of c, if that makes any sense. Right? It's the notation way of explaining it. All right. Same as, so I'll say same as f of c. All right. Then it gets a little tricky, right? You have two possibilities. All right, so it could be, so in the second part, if the result exists, then that is your limit, is the limit. All right, so exists as in it's defined, it's not imaginary, you know, it's an actual number, right? If the result, I'll give the result is undefined or imaginary, simplify f of x and substitute again. All right, so that's going to be the case where you substitute that limiting constant in again, but this time into the simpler form of the expression. Then you basically go into that neck of the woods where, all right, well, that result can either exist or not. If it still does not exist, if the limit still does not exist, let me say DNA. All right. I'm just going to shrink to fit here a little bit. A little y came along for the ride. I don't like that. Out of your y. Over. All right, so substitute the limiting constant into f of x for x. The notation wise, that's the same as saying f of c. If you get an answer, if you get a nice clean answer, that's your answer. That's the limit. If you get something undefined, imaginary, or something else that's not an existing value, then simplify your f of x and do the process again. Substitute in again and see what you get. All right. So I'll do a couple of examples for you, just so you see the two techniques, but they're pretty straightforward once you get the hang of it. All right. So first off, you're going to identify whether you're approaching infinity or a constant. All right. It's a constant if it's not infinity. All right. So let's just put it that way. So here I have infinity. So I'd be working with this technique. All right. So what I'm going to do is I'm going to take my f of x. I'm going to pull that out. So f of x is equal to 5x plus 4 over x. I'm going to grab the term with the highest power on the top of the fraction and the term with the highest power on the bottom of the fraction. Those two are going to get divided. All right, so my EBM is going to be y equals 5x over x, which simplifies to just y equals 5. All right. That's what we're going to find the limit of. All right. So we're going to look at this and say, all right, well, what is the limit of this? So I'm going to say the limit as x approaches positive infinity, or just infinity, of, instead of 5x plus 4 over x, I'm just going to say of 5. All right. So a nice application, not really application, but it's more like consequence, really, anything else, more than anything else, is that if you're finding the limit of some constant value, you already know the answer. The limit of a constant is a constant, right? And that has everything to do with the general understanding of this idea, because if something is constant, it's not changing. it has a value of 5. It doesn't matter what x is going to be. It's constant. It's never changing. All right. But what that actually gives me is the limit of this whole thing. So this limit, this whole thing here actually also has a limit of 5, or this limit problem has a resulting limit of 5. So 5 is the answer. Now, the question that I would be asking is, how can you just do that? How can I say, all right, forget about the function that they gave us. I'm going to make it my own function. I'm going to come up with my own thing, and I'll just find the limit of that. If that's the case, then math just got a whole lot easier. So there has to be a reason for it. All right. So what I'm going to do is I'm going to type in the original function f of x.
Professor, quick question.
Yeah.
Where does the +4 go? Why is that ignored?
Based on the process here, we're dividing the term with the highest power on the top by the term with the highest power on the bottom.
Okay.
So we only care about those terms. That's it.
Gotcha.
So here's what the original function looks like, and here's what my EDM looks like. They look nothing alike. One of them's a horizontal line, the other is like a funky curve. But for extreme values of x, so going out to negative infinity, going out to positive infinity, they behave the same way. All right, and I can justify that. As we go out to the right, the red curve is almost indistinguishable from the blue one. Right, so for large values of x in the positive direction or in the negative direction, the behavior of the graphs are the same. Now, towards 0, they don't behave at all alike. But for extreme values, they behave very much alike. Right? So we have the ability to say, okay, wherever the end behavior model goes, the original function also has to go there. It has to go, it's got to get to the same destination. So if the limit of one is 5, the limit of the other is also going to be 5. All right, the second example is basically the same idea. So we look at an end behavior model for this function f of x. 2x over x plus 4, the term with the highest power up top is 2x. The term with the highest power on the bottom is just an x. So my end behavior model is y equals 2x over 2, which is just y equal, I'm sorry, 2x over 2, 2x over x, which gives us y equals 2. And I wanted this to be a colon. So the process is telling me, all right, I don't want this crazy function. If it's going to behave the same way as this function, I'd rather use the easier one. So I'm going to say the limit as x approaches negative infinity of 2, constant never changes. So limit as x approaches anything of 2 is going to be 2. That's the y value for all time, right? Because these two are equivalent for large values of x in the positive direction or in the negative direction, they must then have the same limit. All right, there's shortcut rules when it comes to finding limits, but this is the best way to go, not because it's the way I'm teaching it to you, but because this is the way that gets at why things work the way they work. All right, you think about the behavior of different graphs, like for example, let's take a look at number 5. Oh, by the way, number 3 is a trick question. There's no fraction there, so what would you do? You know, I'll get to that one in a minute. But looking at number 5, I could put in the original function, x squared minus 2 over x plus 1. We'll find the end behavior model. So f of x, again, x squared minus 2 over x plus 1. The term with the highest power on the top is x squared. The term with the highest power on the bottom is an x. So y is equal to x squared over x, making y equal to x. So this graph, the one that I plotted already, is going to behave exactly the same as this graph for large values of x in the positive or negative direction. So what I'll do is I'll graph y equals x. I'll plot that, get that curve going there. You see they don't look anything alike around 0. But as I go out to negative infinity, which is what this question is asking me to do, you see that those graphs are behaving the same way. All right. So that red curve, the original rational function, is taking on the properties and characteristics of a linear equation for large values of x in the negative direction. All right. So wherever this one goes, this must also follow. So then what I would do is find the limit as x approaches negative infinity of the end behavior model, which is just x. Now, this isn't a constant anymore. So we got to do something different. Find the limit of the end behavior model by substituting the limiting value c for x. All right. So this is my c right here. Even though it's not a constant, we still use c to represent it. Every x in my end behavior model, there's only one of them here, is going to get replaced with that c value, in this case, negative infinity. So this limit is negative infinity. Because this limit is negative infinity, this one must also be negative infinity because they behave the same way for extreme values of x. All right. The remaining problems, with the exception of number 3 on this page, are essentially the same idea. So I'll leave you to try those. But I wanted to go over, well, I'll save 3 for next time, but I wanted to go over some analytic cases involving a constant. Right. So that's on the next page. It crashed. Come on. It'll say it's optimizing. And then it'll come back to the wrong page. All right. In case you wanted to know what I was doing in Algebra 1 today, there you go. So on to the next page. I'll just do 2 problems, one very easy and one a little bit more complicated. All right. So taking a look at number 1, very simple. The process boils down to you have a limiting constant. We're going to replace every x in the function with that limiting constant. In this case, there's only one of them, so there you go. Simplify. If you get an answer that exists, then that's your limit. Negative 3 plus 4 is 1. That exists. 1 is a value that exists. It's not undefined. It's not imaginary, nothing like that. And so there you go. That's all there is to it. Right? But if you take a look at number 6, and I'll save the trig ones. I'll do all the trig ones next class in one shot. This will be the last problem we do tonight. If you look at number 6, I can try that technique of plugging 0 in for each of the x's. If I do that, 0 plus 2 squared minus a 4 over 0. 0 plus 2 squared is 4, minus 4 is 0, 0 over 0. That's what's known as indeterminate, right? Indeterminate can mean a lot of things. But in this context, it means that there is a limit that can be found. You just have to do some algebra to get it, all right? So what we'll do is we'll simplify this function. Sometimes that'll require you to factor. Sometimes it'll require you to distribute. This one's already in a factored form, so let's distribute it out. If I distribute x plus 2 squared, I'm going to get x squared plus 4x plus 4. Everything else would stay put. But now I see that I have a 4 and a -4 that would cancel out. So I'd have x squared plus 4x over x, which simplifies further. I can factor out an x up top, or you just cancel it straight away. That's up to you. But I can cancel these x's now, and now I have an equivalent expression. Limit as x approaches 0. Instead of this big old mess here, I have just an x plus 4 that'll accomplish the same goal, because it doesn't matter whether or not there's an actual point at the location. It just matters that you can identify the location that the graph is approaching as x is getting closer and closer to 0. So now I would substitute again. I would replace my x with a 0, simplify, and get a 4. Right? 0 plus 4 is 4. And so that is the limit of this problem, but it also means that it's the limit of this one. So equals 4. And that's ultimately what we're looking for, the limit of the given question, not the simplified form. Right? So I really shouldn't have even boxed this. All right. So this would be our final answer. All right. So it's a lot to digest. We covered a lot of different concepts today, but hopefully you'll see that they're all kind of coming together and building off of one another. And in fact, if you were to graph this one, you would see that it's another instance in which there's a hole in the graph. So it's pretty interesting from that regard also. So at this point, I'll let you all off the hook. I'm going to stop the recording.